In order to access the QC software in operator mode, just navigate to the KLIPPEL QC Start operator link on your desktop. In contrast to engineer mode, most of the settings are hidden here, and basically this tool helps the operator to find the right test sequence. Using the barcode input, this can be even automated. If the barcode mask has been set up correctly, you just need to scan one of the device under test labels, and the test will be selected automatically. Just hit enter to log in. Since the engineer has set up user administration to make sure that no test settings are changed by operators and only dedicated persons are allowed to log in and perform testing, we need to enter the user credentials here. The operator testing user interface is kept pretty simple. We basically have only a control panel with some buttons for the main functions such as starting the test, entering the serial number, calibrating limits or manual sweep diagnostics, and we have some result windows that show all the parameters that the engineer has set up for the test. A measurement can be started by entering a serial number here in the serial number input field and hitting enter. I will be using the QR code label on the device to scan the serial number. Then I just hit enter. As we can see, this unit has passed all limits and even all grade limits, resulting in an overall grade 1. So let's repeat test for this unit a few times to see how fast the QC test is and to see how reproducible our result is. Using the repeat functions, the logged results are always overwritten with the same serial number. This means our pass-fail counter is left untouched when repeating a measurement. Now let us continue with our next speaker. This one is also a pass. Our online yield is still 100% for each tested parameter, and our overall pass counter has been incremented. Let's check out the next unit. As you can see, this unit has failed the rub and buzz limits by a few dB. It seems like a mechanical defect. For manual diagnostics, we can use the manual sweep feature in combination with the headphone aurotization of rub and buzz distortion. As soon as we hit this button, the live scope will open and we can listen to the isolated effect signal. I will use the manual sweep controller to modulate the excitation frequency of the sine tone in order to spot the most critical frequencies and listen to the distortion patterns. As you could hear, the impulsive distortion patterns coupled to the excitation frequency were quite audible. So this is most likely a mechanical defect of the drive unit. As you can see, the rub and buzz curve is a very sensitive means to detect any kind of abnormal impulsive noise and distortion caused by loudspeaker defects. But what happens if we add some ambient noise disturbance as caused by a dropping hammer in the production floor? I will simulate this by dropping a piece of metal on the floor during the measurement. As you can see, the ambient noise heavily impacted the measurement. The rub and buzz results are far beyond the limit caused by the loud ambient noise disturbance. However, We don't get a fail verdict here because we have our second ambient noise microphone that has monitored the measurement in parallel. We can make the ambient noise response visible in this chart by right-clicking Show All Curves. We can see here that we have rub and buzz noise curve here, and it follows the rub and buzz reading inside the test chamber pretty closely, and therefore our limit detection algorithm could pretty clearly identify that the disturbance came from the outside and this is not a failed unit. For this reason, we have the noise verdict here. In this case, the operator can just repeat the measurement so this measurement was free of disturbance and we get a pass finally. The ambient noise detection is a feature of the QC standard software. However, the production noise immunity is an add-on module that enhances the ambient noise detection by an automatic repeat and merging technology in order to have valid test results even if you have frequent ambient noise disturbance. So what can we do if we have some systematic changes in all our unit's responses, maybe due to a change of the test box design, microphone placement or ambient conditions? This unit here is supposed to be a good unit, but it fails the limits. So we can go back and remember our golden unit that we found in the limit calculation mode. We can use this unit to monitor the difference in all the responses and adjust the limits accordingly. In order to do so, we need to mount the golden unit and hit the Calibrate Limits button. After measuring the golden units, the limits have been adjusted automatically. You can see in the normalized frequency response view that we have a perfect flat line now. We also get a warning here that the calibration deviated considerably from the reference units, mainly related to the third harmonic. We could see that earlier because we even got a fail for the third harmonic related to the drop of the frequency response at low frequencies. However, we accept that and we can continue testing with the new limits right now. So the test run verified that our limits are adjusted perfectly now. If we want to restore the original limits, the engineer just has to go back to the limit calculation mode and click Calculate.